Looks like it's time. Welcome back, everyone. Probably the bigger announcement, aside from all the stuff we see here, is that the exams have finally been graded. Thank you for your patience on that. It was definitely a little bit longer than usual on this third set. As far as the exam, let's take a look. The summary statistics are average grade was 78.5%. Maximum grade came out to 95.08%, so above 95%. And just like the other exams, you have a fraction here for your exam score. It turns into a percentage in Moodle. And your running course score is also provided here. So now this is the average of exams 1 through 3, as well as your quiz grade, as well as your homework grade, all rolled into one spot. So that's how you're doing in the course so far. Well, any questions, folks, about the exam while we're taking a look at it? I think I do have one comment I want to scroll down to while you're thinking about it. There it is. I made a mistake right here. Sorry about that typo. I put on problem number 4, part A, describe the unknown population characteristic P. It should have said parameter. And since that was my mistake there, and I think it is a serious typo, I didn't take off any points from anyone on this exam on part A there. It just wasn't a totally fair question because of that. Yeah, you bet. For me, these are tough typos because population characteristic is completely synonymous to parameter, but we're not expected to know that. That was a whole different book I was reading, not you folks. So again, sorry for the distraction on that one. Aside from that typo there, or just really rather a mistake in the verbiage on problem number 4, the problems that folks would like to take a look at?
Number 1.
Yeah, absolutely. So problem number 1, looks like this one was a regression problem. After importing the data, the model should have came out like this. So y hat is 127.24 minus 1.11x. Any questions on getting the y hat expression?
Where did you get 127.24?
It's something that calculator pretty much just spits out at you. So after importing the data here and here, that should come up. Let's actually pull this out to actually really properly address that question. Instead of saying the calculator spits it out, I don't know if that's the best answer. Let's clear that out and go to, I'll hit the stat button, enter to edit, and it looks like we've got random stuff in here. So 50, 60, 70, 80, 90, 100. That's kind of nice. Okay, so those are our dive depths, it looks like. And then for L2, we go 80, this is a little bit more random, 80, 55, 45, 35, 25, and 22. Okay, I don't know how legit those numbers are. Scuba diving is a dangerous and precise science, so definitely don't run with that data. But now that's in the calculator, hit stat again, move over to calculate, and I believe we're on option number 8, linear regression. So after you get to this stage, the calculator is going to spit out this information. The model is y equals a plus bx. So in place of a, the calculator indicates 127.23, so I rounded up to 24. And in place of the b, we have a negative value, so I wrote in negative 1.11, rounding to 2 places. So that gets us our model going on that one. Any questions, folks, with that step there? Okay, then going through the problem, as far as the slope goes, a lot of people wrote this part, but you had to say for each additional foot, so the amount, the dive depth goes down by, you have to say the number of minutes right here as well, tying the context together with the depth. So the denominator was for your dive depth going this way, sorry, horizontally, and the numerator is the amount of time decreasing by 1.11 minute for each additional foot. So I feel like part B was a pretty tricky question, but they usually are. Part C, people did pretty well on. So all we had to do is throw in the dive depth of 88 feet in place of X and just crank it out. The model says it should be about 29.56 minutes. And there's a double check you can make here. The actual value between 80 and 90 feet is 25 to 35 minutes. So your answer should be somewhere in that ballpark. For example, we got, say, 295 minutes. That would have been way out of our expectations for these values here. The next trickiest question was definitely the y-intercept and its interpretation. At a y-intercept, you have to plug in a value of 0 for x. And so in this problem, it did not make sense to interpret the y-intercept, because if you do plug in x is 0, you have 127 minutes, but that means you're diving at a feet of 0 feet. That could be a massive head injury, but the amount of oxygen you need would be infinite, right? There's no dive time if you're not diving to any depth. So that was the idea with the last part down below here. Well, any other questions, folks, with that problem one or other problems to take a look at? Oh, gotcha. That's frustrating. Sorry about that. Okay, well, as far as exams go, keep in mind that the course grade that I put on your exams, the same thing that's under here under grades on Moodle, is something that changes a lot from question to question. Yeah, absolutely, Braden. Let me pull that up again. And as far as where we're at in the course, the way I gave you your course grade for after exam 3 was all of this is your average grade for exams, so 65%. But once we go to take the actual final exam, it changes a lot. So if you had a bad exam, that's going to be kind of diminished to a certain sense. And we have extra credit that goes along with the final exam as well. But let me take a look at that question, number 3 on the exam. Thanks for asking about that one. Let's see here. This is a good time to do an exam review since we don't really have a lot more time left in the course. We're probably all thinking about reviewing for the final exam, and this is really excellent review. The solutions to all exams are posted in Moodle, so you can take your old exams and use those to study for the final exam as well. And question number 3 goes, well, this was the probability one. So they give us 3 probabilities. B is having a complimentary breakfast at probability 0.83. F is having a fitness center at probability 0.53. And having both amenities, it came out at 38%. So probability of both B and F was 0.38. It looks like I solved this one without the use of a Venn diagram, but folks that used it didn't do too bad on that either. Let's throw one down on here just to have it. While we look at this problem. So we have B for complimentary breakfast. We have F for the fitness center. Let's see, we have probability 0.38 in the middle for both amenities. This is the stage at which I would need a calculator. So for this region here, probability of B excluding F, we would take probability 0.83 minus 0.38 to give a probability of 0.45 going right here. And then do the same thing for this region. So probability of F excluding the overlap for B would be, let's see, probability of F is 0.53. Subtract the overlap, 0.38. We have probability 0.15 in this region. We do want the last probability, the one that's inside neither bubble, B nor F. So we go 1 minus, and just all of these 3 values here, minus 0.45, minus 0.38, and minus 0.15 gets us to a meager 0.02. So this is just one way to attack the question, but if you decide to go this route, notice that this probability 0.02 is the probability of having neither the complimentary breakfast nor the fitness center. And so that's how you can get probability 0.02. So one way is through just this Venn diagram. In part A, when you're calculating probability B or F, I indicated it by using the formula right here. It came out as a 0.98. But if you use the Venn diagram approach, you would have taken 0.45 plus 0.38 plus 0.15. Let's just do that here for illustrative purposes. 0.45 plus 0.38 plus 0.15. And that comes out at the same value, well, it's supposed to. Let me try again. It works if you put it in right. Let's put a dot right here. Okay, that's now a 0.15. and it comes out at probability 0.98. So either the direct formula or the Venn diagram analysis will give us that value there. And by the way, now that we've calculated it, probability of E or F, this is the probability of having a complimentary breakfast, a fitness center, or potentially both. When we say oh, both or both, we're referring to that 38%. As far as the rest of them go, part B was a complement rule, so calculate probability B complement. We use the fact that probability of B is this 0.83, so go 1 minus with the complement rule, comes out at 0.17, and that tells us then there's a 17% chance that that event doesn't occur, which would then mean your hotel does not have complimentary breakfast. That's terrible. That's a pretty high probability for a horrible event, but that's what this would say here for that probability. And then likewise, this last one right here, if you didn't do a Venn diagram, you would go up to part A. This is having a complimentary breakfast or fitness center or both. So the probability of having none of that would be a complement rule. You would just go 1 minus your answer from up here to get the 0.02. If you use the Venn diagram, the answer is just right here. You would just have to cite it. This one didn't need a practical interpretation, so the number 0.02 gave you full credit. Any questions at all, folks, on maneuvering through that one there? Okay. Well, any others that folks would like to take a look at? Yep, absolutely. Thanks for asking about that one, Braden. Okay, well, if there are further questions, don't hesitate to ask in office hours, after class, before class, that kind of stuff. I'll be happy to help out. And if you don't have, or if you're not here today to get your exam back, don't hesitate to send me an email. I don't have any qualms of scanning this and just sending it to you that way. Well, with where we're at so far, we still haven't gone through any of the announcements, but that's okay. We'll get there. Let me see how back this undo procedure goes. Yeah, it goes pretty far, actually. So we are currently, to get the scroll right, here, there we go. So quiz number 10 is going to be our last official quiz of the whole semester, only because I really don't like to assign a quiz over a Thanksgiving break. That has a really low success rate of getting them back sometimes, which I totally understand. I am thinking about posting an extra quiz down here regardless. It's just going to be an extra credit one. So I'll post it there and post the details as well. The extra credit quiz would be relative to section 15.3 most likely. Then we have no classes whatsoever next week, nor office hours. I still check my emails habitually. So if you send me an email at any time of the day, I'll always be checking them on the morning, and I'll be sure to go through the whole set. No worries if you send me lots of questions. That's going to be just fine. And going even further down in this document, there's a couple extra credit opportunities I want to talk about before we get going with class today. First is this one down here. I just put this extra credit opportunity pretty much for all my classes these days. And the idea behind this one is, if you had a rough exam, maybe it was an off day, something like that, one rough exam really shouldn't punish your score too much by dropping it a letter grade. And so there's a way to make that up. If your final exam grade is larger than your grades amongst exams 1, 2, and 3, your final exam grade will replace it. So just for the sake of just some random numbers for an explanation, let's suppose the final exam grade came out at 82.3%. Exam 1 was 98.3. Exam 2 was maybe 96.7. Exam 3, maybe this one came out as 76.2. Then this one would be overwritten with 82.3 is how the extra credit opportunity would work. And this extra credit opportunity can't hurt your grade. So if your final exam was, say, 60.3, none of these would be affected. You'd still keep those old scores. But again, that's a way to make up a credit. Maybe something went crazy on the calculator that dropped your grade a lot, or something just random happened. Like I lost control of the scroll here. That's a way to get some credit back on your exams. And it's another way to give extra credit along the lines of maybe you just weren't very caught up on exam 1, but if you showed that you got caught up on that material through the final exam, it can increase that score again. Not necessarily exam 1, but your minimum score amongst that list. Any questions about that so far? Okay, the second extra credit opportunity, well, really the first one on this list right here, is about the course evaluation. Course evaluations have been really hard to collect for the math department. We're really not sure exactly why. So I've changed a couple things. I've been giving extra credit opportunities just to try to get course evaluations. And I also put the link directly over here. The where it's supposed to be is there. I don't know if the people knew you could open up this menu bar, but the course evaluation is typically here. And most of your classes, it's actually on the very, very bottom. I moved it up to the top just to make it visible in this course. But then I realized you could just put a link down. That might be the best way to go. So the way this extra credit opportunity works is, if you click on this link, it tells you the reason we do a course evaluation. Our boss's, the State Board of Education, requires it in Idaho, so we just have to. There's no questions about it. It's a firm requirement. It's actually really important. It's how instructors, the department determines how well is the class going. For example, we did an ISU book bundle. I'm sure a lot of people would want to comment on that kind of stuff, how it affected the classes, not just in this class, but any class. Anything else you'd like to think about that could help out with as a comment would be really helpful here. It takes about 15 minutes is what they say. Just depends on how much time you want to spend on it. If you click on this, answer the questions, now you're getting going. I can't actually do this evaluation, so I'll back out of there. But once you complete all the questions and hit the submit button, it takes you to the thank you page that just says, thanks for submitting the course evaluation. If you take a screenshot of that page, email that screenshot to that email address, the same one a lot of people send their quizzes to, then that gives you the extra credit of dropping an additional 2 lowest grades in my lab, for a total of 4 would be dropped in the semester. I'm going to double check that. I think I told the class we're dropping 2 by default. I'm going to have to check my notes on that. But this will give you an additional 2. So it's a pretty fast activity, but I've actually had a complaint about this. The rough thing about this is an extra credit opportunity is that the math department will close the course evaluation for real on December 6th, Friday. So this is one of those things where you have to act while you can act. If you go to do it on Friday, you might not have the opportunity to actually collect that extra credit. That's a lot of announcements so far today, but any questions so far? Okay, again, we're going to post another additional quiz here as well for another extra credit opportunity. And really all of your quizzes, their whole purpose is to get us going on the final exam. Oh, I thought I put some final exam information there. So I'm going to have to come back to the drawing board on that. As far as the final exam goes, you know what? We're all here right now. Let's just post it in. As far as the final exam goes, oh, that's weird. Hang on. I think that's why that messed me up. This is not finals week. No, it's this one. And I just want to, I can't seem to add anything to that week. I'm going to have to go back in there and fix that. But what I was going to write in, once I am able to move this, there we go, was that the final exam is on Monday, December. Yes, absolutely. So the 9th of December, and it's going to be in CHE 215. That's here. That's where we're at currently. It'll be from 5:30 p.m. That's the good news. It starts at our normal class time. It's in our actual room, but it goes to 7:30 p.m. So it's a 2-hour exam. It's going to be representative of all the information we covered in the course. I can't ask every single question because that would be a really long exam. But one comment I was about to say is you could put all your old exams together. That's a pretty good final exam review. I'll have extra information here as well for the things that wasn't on exam 3.
Will you put blank in there?
Yeah, absolutely. You could also take all of your quizzes as well, put them together and use that as its final exam review. And just like you mentioned, actually do put those blank quizzes together and just make it one packet of a worksheet.
Will we have a review day before then?
Yes, absolutely. I believe we're reviewing on, let's take a look here. So we have a normal day on the 2nd, But then we'll be reviewing on the 4th and the 5th likely. So at least 2 days, probably finishing off whatever topics on the 4th and then segueing into reviewing. Other questions at the moment?
After that Monday, do we still have to come to class on Wednesday and Thursday?
You do not, yeah. So that's really officially the last day of the course altogether. And you know, I'm glad you mentioned that, since another thing that happens on this Monday right here, it being the last day of the course means this is the last day to turn in quizzes and to work in my lab, the homework system as well. So that's essentially the last day for everything, pretty much. Other questions at the moment? Okay, thanks. Those are really good questions about the final exam. Sorry, I forgot to put down the information here. I'll get that posted soon. And once we get closer to this week over here, oh, sorry, I missed that question, Tiffany. I don't know how many questions, but typically it's around the order of about 10-ish questions altogether. And what I'll be doing to also give a good indication of what the exams look like is, before going on to the Thanksgiving break officially, on that weekend, ahead of that, I'll be working on updating this, providing the sample exams, the same kind of stuff that you would expect if it were like an ordinary exam 4 in class. Sort of is, it's just the final exam and it happens to be 2 hours. But we'll be doing the same kind of stuff, posting that information. Any other questions at all, folks, so far? Okay, well, with where we're at so far, we are right here, section 15.3. This is hypothesis testing for a population proportion. And then if we have enough time in the course, we'll move over to section 15.4, hypothesis testing for a population mean. 15.4, if we make it through that content, will be the last official section of the entire course. But like anything else in this class, you never want to rush these things. So we're going to be working at this at a normal pace. So here's where we left off last time. In example 1, we're looking at a problem that has to do with National Center for Education Statistics. They are telling us that in 1996, 34% of the students had not been absent from school even once in the previous month. But then they took a survey of 8,302 students, and this is in year 2000, so 4 years later, and found that that proportion slipped down to 33%. So it actually went down a little bit. But we know from statistics, that's not enough to get excited. That doesn't mean there's a real effect in the population. We either have to conduct a confidence interval analysis to see if something is really going on, or like in this problem, we're going to run a hypothesis test analysis. So these are the hypotheses that we actually put down in section 15.1. The null hypothesis is the hypothesized value. It's a statement that everything is the same, nothing's changed about the population. Still 34% of students have not been absent at least once in the last 30 days. But we're testing this alternative hypothesis. We found that the sample data had a figure that's slightly less. So this is directly asking the research question, in 2004, has that proportion gone down below 34%? Here, we also have the population proportion indicated this way. Let's highlight that. The same proportion that we indicated in section 15.1 as well at the end of the notes. So the way we start testing these hypotheses at the significance level alpha is we do another z-score essentially. The z-score is going to measure the number of standard deviations, the statistic p hat, is away from the hypothesized value, 34%. So we calculate it this way. Even though it's officially called the test statistic, it is still a z-score. It's measuring the number of standard deviations. And notice when we go to calculate the standard deviations, this came from the central limit theorem, but we made a huge assumption. We assumed that the true population mean really is 34%. So we plug that into this. That's why we're not calling it a standard error any longer. If the null hypothesis is true, that is the exact standard deviation. So we plug it in right here in our z-scores. We have this value, 0.0052. And now we know that this value, p hat at 33% is almost 2 standard deviations from the value in the null hypothesis. That's pretty far away. If the probability of that happening is below 0.05, we will reject the null hypothesis. So that's essentially the logic of hypothesis testing. Let's put that down on paper, actually. If the probability that p hat is more than, let's say it this way. If p hat is below 1.9231 standard deviations away from p naught equals 0.34 is less than this thing up here. We called it the significance level alpha, and that's the decider of the hypothesis test. It's the amount of evidence that we wanted before we reject the null hypothesis. And the smaller it gets, the more evidence we require. So if the null hypothesis is a really, really impressive claim, this should be a really, really small value, since impressive claims require lots of evidence. So if the probability that we're more than further below the 1.9231 standard deviations from p naught, if that probability is less than alpha equals 0.05, then we reject h naught in favor of HA. We will have found significant statistical evidence that the alternative hypothesis up here is actually true, that the percentage really has gone down in year 2000. So that takes us to this step, calculate the p-value. So notice the p-value is kind of meaningless unless we know how much evidence we want. The alpha value is kind of like the level of confidence in a confidence interval. And we mentioned before that if you have a 90% confidence interval and you decide to do a hypothesis test, it should be at 0.10, 10%. Likewise, 95% confidence is conflated with 0.05 for the significance level, and so on down the line. These values should total to 1, and if you do that, your two-tailed test gives the same analysis as the confidence interval. Fortunately, this is not a two-tailed test, so the confidence interval could give us a conclusion that runs different. So we're just going to stick with this analysis right here. So here, we're going to calculate the p-value for this test. Any questions first, folks, before we start to delve into the further content? Okay, let me scroll for just a moment to right to this part. When we looked at these tests, we said that this one is a left-tailed test because of the less than sign right there. So let's re-mention it right here. We have a left-tailed test. Now, we're very interested in the test statistic, Z. This comes from the normal distribution. So now the picture looks like this. Here's our normal curve. The way we indicate that is a capital N to say this is a normal distribution. Then we give two numbers. 0 is referring to the mean of this distribution. It's been a while since we looked at this, so think of this as kind of a review for this portion of chapter 5. The value for sigma is 1. That's the second input. So here's sigma. The reason the mean is 0 and the sigma is 1 is because the z-score has standardized values. It's subtracted the mean, so it's now 0. It's divided by the standard deviation, making it a 1. So there's our model, N0, 1. There's 0 right here in the middle. And next thing we want to put down is the z-test statistic. It is at value negative 1.9231, so it would be right around here. That looks like about 2 standard deviations away. Negative 1.9231. Now recall with the normal distribution, if you put a vertical line segment here, and ask the question, what's the probability z is directly equal to negative 1.9231? The probability is 0. It's kind of shocking. Probabilities under the normal curve come from areas, and the area of this vertical line segment is 0 because it has no width. That's why we said right here, the probability p hat is below the 1.9231 standard deviations. I should have put a negative sign on that. Sorry about that confusion there. If it's below that, that's how we find our probability. So the left tail test is saying, go to the left of your test statistic, which means your probability comes right here. If it was a right tail test, we'd be taking the probability on the right of z, even if it's negative. So wherever z is, we want the area on the right. So left tail test says you want that area. That area is now the p-value. And we could definitely do that. That's really just a chapter 5 problem. Finally, this part of the notes does answer a lot of questions. You might have been wondering, why in chapter 5 did we do a z-score? It was just so we could calculate a test statistic and know what we were dealing with. And, well, we did a lot of other stuff in chapter 5. The reason we work so hard on this picture is it helps a ton with the hypothesis test. And now another question we have to ask is this normal CDF or is this inverse norm? To get that area there. Turns out it's not inverse norm. It would be a normal CDF, yeah. So this one will be using normal CDF. So back to the calculator. Here's how it goes. First, let's put down what we're about to calculate. We're about to get the p-value. So this will be our very first one. That's pretty exciting. In your calculator, hit second and bars. Go down to normal CDF. And honestly, if you aren't too sure, say this is a real exam and you went to inverse norm, you know right away that something is not quite right because we don't have an area. So that'd be our indication. Hit second quit to get out of that menu. Second bars, back to normal CDF. And, well, if the area is going to the left forever, we use negative 10 power 99, or we could just let the calculator express it their way. Let's actually throw this on the notes just so we have something definite. Input 1 is going to be negative 10 power 99. So that's for the lower. This is input 2, upper. And then mu and sigma actually have labels, so we don't necessarily need to be that specific. So negative 10 power 99 for the lower. Upper value is the test statistic, negative 1.9231. So your calculator should look just like this. Be sure to make mu 0, sigma 1. The values are changed for something else. And altogether, this is what the p-value should come out as. It is a 0.0272. 4 decimal places is pretty standard to round for p-values like this one. So 0.0272 is our official answer. Well, we got it, folks. That's the p-value of the test. We now have to decide what we're going to do with the hypotheses, whether we're going to reject them or fail to reject them. But any questions at all getting to this critical step here? Okay, so we analyzed the left tail test. Tricky thing about this is there's really 3 tests. There's a right tail test, the left tail test we see here, and the two-tailed test. And getting the p-value is slightly different in each one of those cases. That's one of the reasons hypothesis testing goes a little bit slower than confidence intervals. There's a lot of extra stuff to just describe and get through. But let's take a look at this p-value and do one additional thing with it. It is a probability. That's why we call it p for probability. But it's a very tricky probability to say exactly what it's actually expressing. So let's put down here in words what this says. Assuming H0 P equals 0.34 is true, We have to make that assumption. That is step one in a hypothesis test. You assume that the null hypothesis is the reality about the population. There is a 2.72% chance that, so what I've done here is just taken the p-value, convert it into a percentage. It's typical thing we would have done with a probability. So there's a 2.72% chance. Let's come up here, grab this information. This is a temporary screenshot. So if the null hypothesis is actually true, that the true proportion is 34%, but our data got 0.33 for the sample data, we can say 2.72% chance that the data is as extreme as p hat equals 0.33 or more extreme. The or more extreme is like your test statistic z going off to the left. That's where we calculate the area going to the left forever on that left tail test. So altogether, there's only a 2.72% chance that your data came out this way or worse if this is the truth about the null, about the population, only 34%. So that's a pretty low chance. And we also said at the very beginning, this was set up. Significance level alpha is at 0.05. Let's actually move out to here before we take that. So even though that probability looks low, to some people it might not be. It all depends on the context and how the study was written at the very beginning. When people go to write a study involving a hypothesis test, they have to first say what the parameter is, what the null hypothesis is, what the alternative hypothesis will be, and what the significance level alpha is. Before even gathering any data, all of that has to be submitted. A lot of times you're submitting that to like the federal government if they're funding your study. Then after you collect your data, no matter how upset you might be about these hypotheses, you have to stick with them. Nothing can change. So if this was, say, 0.0272, but we made this a 0.01, that's not good. We would have failed to reject the null hypothesis. We can't move that up to a 0.05. But that was the real value that they gave for us. So that means 0.0272 is small. Let's say that here. Since alpha equals 0.05, the p-value, 0.0272, is small. So what we mean by small is below whatever alpha is. So there's only about 2.72% chance of obtaining data as extreme as what we obtained, or more extreme. We can now say here, because the p-value is 0.0272, it's less than the significance level alpha, we will reject the null hypothesis. Let's say that here. Since the p-value is 0.0272, and it's less than 0.05, which is the significance level alpha, we reject H naught, all because of this right here. Our p-value came out less, is leading to that rejection. And just as a reminder, there is a table up there in the notes. Let's just take a quick gander at that. P-value less than alpha means rejection. Greater than or even equal to alpha means we would fail to reject. We wouldn't have evidence that the alternative is true. So that came from this table right here. And now we're doing the trickiest part about part C. It says, give a practical interpretation using the context. This right here is not the practical interpretation at all. It's a probabilistic one. And it's one of those interpretations that even as a statistics student, I think this is a tough interpretation. I remember being a student in this class and not quite getting it the first time I saw this. So what we're giving here is something entirely different. This is like what a reporter would say at the conclusion of the study. So it's an interpretation that anyone can understand if you've taken statistics or not. So here's how it goes. We said right here, we're rejecting H naught. There we go, it's gone. That means the truth about the population is this one, and we have to say exactly what that means right here. Let's begin by saying we have significant statistical evidence that, and this goes very similar to confidence interval conclusions. We're saying we have significant evidence because we did reject the null hypothesis. So we have evidence in favor of the alternative. And we just read out what this says. P is the proportion of all students. I'll abbreviate this a bit and just say that have not been absent in the last 30 days. Okay, so we read out the parameter P. Next thing we say is less than, it's a left-tailed test, so we have to say that eventually, is less than. Then we go over here to the hypothesized value and just read it out, 0.34. So we have evidence that this alternative is true. All we just did is write out what it really means. In place of P, we just put in this highlighted version here. And then for the less than 0.34, we pretty much said that verbatim, just without an inequality sign. Well, any questions at all, folks, with the conclusion here? Okay, so for these data, there really was significant evidence that the figure has slipped below 34%. We now know it's below 34%. And it's a good idea to pause right there and think about hypothesis testing. It's great in a way, but if you tell people we have evidence that the proportion of students is below 30%, they'll say, great. What is it? They want an estimate now. The follow-up question is now a confidence interval is what you would have to give them. So hypothesis testing in a class like this feels like it's something totally different than a confidence interval. That's not really the case. These methods sometimes go together. A lot of times both methods are given at the same exact time. But let's take a look at a totally different reality. Suppose for some reason the study actually was done differently. Now you can never do this after the fact. If this is a study for the federal government, you've probably broken the law and committed fraud because you'd agreed not to do this. But you can never change your significance level alpha. So this is hypothetical now. We're saying suppose alpha is instead 0.01. And that would make sense because this is talking about all students in the nation. Any claim that you make here in the conclusion of the test can actually influence public policy. It could change how things are funded. All sorts of things could happen in the federal government. So it makes sense you would like a lot of evidence before you start making big changes. So that's a pretty appropriate value. Let's suppose it was the real value. Take another look at our p-value. Let's see what would happen in this case. So part EC is done, and this is very atypical. For example, one, we're looking at two different realities. In part D, we're imagining what is the conclusion if we fail to reject the null hypothesis. And that's what would happen this time. It asks if instead the significance level is 0.01, would we reject the null hypothesis or fail to reject it? Well, we would say here that 0.0272 is bigger than 0.01 equals alpha. And then that would imply very next, we will fail to reject H naught. The failing to reject is from this part right here. Our p-value is greater than so we can't reject the null hypothesis this time at all. Does that make sense to folks on this one? Okay, just to see both at once, the prior problem, when we had the significance level set the way it was originally, it was less than gives us a rejection. And the greater than here, let's say it this way, greater than or equals, if it had come out that way, greater than or equals leads to failing to reject. So now we need to know, how do we write our conclusion this time if we fail to reject the null hypothesis? The one thing that we need to be really careful of, it's actually pretty easy to actually slip into this temptation, is the following. We cannot write a conclusion that expresses H naught is true. That deserves an exclamation mark, because again, that's something that feels really awful about hypothesis testing. If we fail to reject the null hypothesis, it doesn't mean we're accepting the null hypothesis either. Just like in a court of law, if someone has not been found to be guilty, we did not prove that person's innocence. The person's innocence is not what was in trial. It was what was initially assumed in order to gather evidence. Here, we initially assumed that's true, so we could come up with the p-value. The probability of getting the data as extreme as we got, or more extreme, when that's actually true. But just because we failed to reject it, did not mean we proved it's true. So we can't write a conclusion saying we have significant evidence the true proportion is still 0.34. What really helps out with this situation is, once again, that table we've been advertising. Let's go back to it. This is not from our book. It's from the book we used last semester, but last semester's book had some really great tables, so I've stolen some screenshots out of there. This expresses quite a lot. It says what to do when you have p-values in these two situations and what the decision should be. So let's place that right down below here. We'll leave this one here as a screenshot, just as a reminder. This is a pretty valuable table. And our conclusion is going to go this way. We're in this situation. So that means we failed to reject the null hypothesis, but our conclusion is going to go this way. We're still going to talk about the alternative hypothesis when we write this conclusion. We will say we have insufficient statistical evidence that that statement is true. So in other words, when it comes to hypothesis testing, the research question is always the alternative hypothesis. That means your conclusion should return to the original alternative hypothesis as well. Either that you found evidence for this, or you just failed to find that evidence. So here's finally our practical interpretation. When we fail to reject, we'll say the study failed to find significant statistical evidence in support of the statement that, and here's the wordy part, the proportion of all students that had not been absent in the last 30 days is below 34%, is what we need to write. So let me see if I can abbreviate that just a touch. The proportion of all students that have not been absent in the last 30 days is below 0.34. And good to emphasize this part. We failed to find the statistical evidence of that statement down below. It does not mean that this is false. It could be very well true, but maybe our sample size was too small to detect that change. Or the null hypothesis could well be true as well. However, our methods don't support proving the null hypothesis is true whatsoever, unfortunately. Let's put a little page break here. I'll leave that table exactly where it is because I feel like this is the trickiest conclusion ever with hypothesis testing. When you fail to reject the null hypothesis, it didn't mean it's true, is the big takeaway. But we did it, folks. That's two potential conclusions. What we'll be doing next in these notes is describing the hypothesis test procedure further. We want to say, how do you get the p-value in any one situation? Then after that, just more examples practicing this procedure. But this is pretty much how it goes, an honest analysis of each of one of those steps you would take. Any questions or comments at the moment, folks, whatsoever? Okay, so this is the land of hypothesis testing. It's a pretty weird way to analyze data, but it is valuable point of view. So here's how the procedure formally starts. This is called the large sample test for a population proportion. And we can use this test if provided two things happen. Part one of the conditions are we should have a random sample, but we know that from statistics. If our sample isn't representative, it's not telling us anything we want to know about the population. And having a random sample is the best way to get a representative sample in the first place. And condition two is a little bit more interesting. The sample size is large, and this condition is met when both np naught greater than equal to 10, n times 1 minus p naught greater than equal to 10. We need to take a look at this a little bit closer. This might seem familiar because it came from 13.3. The 13.3 is a little bit different with condition checking. Let's go down to the confidence interval procedure. It says the sample is large enough so that n times p hat is greater than or equal to 10, n times 1 minus p hat is greater than or equal to 10. These are successes and failures in the actual sample. It goes totally different for hypothesis testing, though. That's really pretty weird. So what happened in hypothesis testing is we go back to this stuff, the central limit theorem. We assume a value for p. Right over here in hypothesis testing, we assume that the null hypothesis is true right away. Did we state that? Let's say it's right here. We assume this is true in hypothesis testing. So if that's the actual truth about the population, we have a lot of extra tools at our disposal out of nowhere. We go n times p naught, and p naught came from here, the hypothesized value. Oh, I lost my red dot. There we go. It comes from right here. So that p naught value is everywhere. It's in fact here and here as well in the standard deviation. So when we assume that's true, we're not looking for the number of successes or failures in the sample at all. This is the number of successes we expect to see when the null hypothesis is true, and the number of failures we expect to see when the null hypothesis is false. Not the actual successes or failures in the sample whatsoever. Let's see if we can add that to the notes too, because I feel like that's pretty tricky. Let's say here as a caution, this condition is different than in chapter 13. So we have a whole different conditions we're checking this time for hypothesis testing. And these are the expected number of successes, failures, forgot a word, successes and failures in a sample size of n when h naught is true. So in other words, just for a quick demonstration, if the sample size was maybe 100, oh, what did I do with my calculator? Sorry. if it was 100 and maybe P naught is 0.25, we would multiply that by 0.25 here. And that would tell us we're expecting 25 successes. 1 minus 100 over here would give us 75 failures. So we're not concerned with whatever happens in the sample whatsoever. We're just checking these two conditions here based off what would happen by our expectations if the null hypothesis was true. So we calculate our z test statistic like we did on example 1, where the denominator is the exact standard error, which we can calculate because we again assume the null is true. The trickiest step then is going down below here, calculating all of your p-values. This is meant to be a big table where you can refer back to it when you're practicing homework questions, quiz questions, or maybe even make a copy of this for your final exam notes to describe where you get your p-values. But I think a lot of people, when you get used to hypothesis testing, you kind of know what to expect based off these descriptions, left tail test, right tail test, and so on. But seeing is believing, so let's write down the pictures for these. Any questions so far before we go down to this table? Okay, well, first is the right tail test. What makes it a right tail test is the greater than sign right here. We still write the null hypothesis in this way in our book, and we're told the area under the z curve, that's referring to the test statistic and the normal distribution, to the right of the calculated value of the test statistic. Okay, so this is what it would look like. Oh, tried for eraser. Let me try again. So if we're doing a right tail test, we'll have a picture that goes like this. This is N01, not my best drawing of it. 0 is in the middle. And our test statistic Z, it can be anywhere for a right tail test. But our hope of hopes is somewhere over here, really, really large. Let's draw it maybe over here. So here's Z. This area shaded to the right is the p-value. And we're shading to the right only because of the greater than sign. So in all these cases, for the p-value, use normal, I think is what the calculator says, CDF. And the input would be this. Z, whatever it is input 1, lower. Input 2 for upper would be positive 10 power 99, because now our area is running to the right forever, not stopping. That's input 3 and input 4 on every one of these tests. So that's the opposite of what we did on example 1. We did a left tail test, so we gathered the area going to the left there. Let's write that out. For the left tail test, still the same kind of picture, another normal curve. Getting better. So here's N01 again. 0 in the middle. For a left tail test, we hope our Z is somewhere far to the left. But it's important to note it could be anywhere. It could be far out to the right here, maybe somewhere in the middle. Let's put it over here. This would be a large p-value. We would fail to reject the null hypothesis on this one. Because we're describing this as a left tail test with the less than sign, this would be our p-value right here, going this way. So that area gives us the p-value, and we would just have to input the right stuff in the calculator. Input 1, lower, this time is negative 10 power 99, the largest negative number supported by the calculator. Z test statistic, whatever it comes out as, is your upper value. It was negative 1.92 on our last example. That made our upper. And input 3, input 4, same last two values of the parameters. So that's how we get our left tail test. We made some curious comments about these tests. We mentioned the two-tailed test is the default test in hypothesis testing. You need reasons to go to a left tail test or a right tail test. And now the trouble with the two-tail test is your p-values are twice as large. That sounds bad in a certain sense, but it's really good in the sense that it means it's harder to reject the null hypothesis. You need more evidence to make that happen. So notice it says twice the area to the right of z if z is positive, or twice the area to the left of z if z is negative. That's what makes the p-value twice as large in the two-tailed test. So in this two-tailed test, let's split it up this way, because there's two things that could happen with their test statistic. Either it's positive or negative. So for this one, let's consider z positive, and the picture would look like this. And 0, 1, once again, 0 here. If z is positive, it would end up in this location, and then negative z, oh, doesn't need a star, sorry about that. That reminds us of confidence intervals. Just z, not without a star. Negative z would be in this location. And in the two-tailed test, you actually want both of those areas. That's why it's called two-tailed. So that's what it would look like if the z test statistic is positive. Let's write down another one. So next corresponding picture. This is if z is negative. So add 0, 1 once again. 0 in the middle. If z is negative, it's got to be to the left of 0. So it'd be somewhere over here, for example. Looks a little funny because we don't know z. As a variable, we can't say it's positive or negative by putting a sign in front of it. But think of it as a negative 1.92 as your z, for example. It's negative, so it's on the left. That would mean negative z is on the right. That looks weird, but that's now double negation. That's the negative of a negative number, forcing it positive. And as before, it's a two-tailed test, so you want the area in both of the tails. So it feels kind of complicated for the two-tailed test. Don't worry, we'll definitely analyze this one. But it's not as bad as it seems. Here's what we would do next. Let me grab a special color. If your z came out positive, that's your positive z, and your input in your calculator should be this for lower. Upper is 10 power 99, and then here's input 3, input 4, and then let's put in another color. Double the result. So in other words, whatever your calculator spits out, you have to double it. So that's what the 2 is here. It's doubling. So the way this works, finally, we can describe is, if you want the area in this tail and in this tail, but your curve is totally symmetric, you might as well find the area once and just multiply it by 2, doubling the result. That gives you both of the tails areas right away. Let's write it down again, just to be completely descriptive, because this is tricky enough a lot to leave it hanging. If z is negative, that means we're focusing on z right over here on the left end, and our information over here will change. We'll say 1 lower is now negative 10 to the power 99. 2 upper is the z test statistic. That'll be input 3, input 4. And this is actually pretty easy to forget. You have to double the area. So in the calculator, double the result. The calculator gives. That's the full description of getting all those p-values. And we're going to look at 1, 2, 3 tests at minimum to see how each one of these goes. Any questions about, folks, with our full description here? Okay, so we finally have the entire, sorry, go ahead, sorry.
Times it by 2?
Yes, absolutely. Okay. Let's actually put one in just as a random example. So let's suppose our z came out, let's say the positive picture. Maybe z was 2.568 is what we found in our calculator. So imagine that value is at 2.568. We'll go second bars, go down to normal CDF, put 2.568 here. Our upper value has to be 10 power 99. 0.1 for everything else. Then that's not the p-value, that's just this area right here. To get this area added in, through perfect symmetry, go ×2 in your calculator, and that's the doubling. That's our true p-value in that case. So we'll practice that in great detail on our next test that's coming up. We have a reminder of that. And they're asking for evidence that something has changed. Example 2 is a two-tail test that we'll walk right into. That's probably good because it looks like the two-tail test is like the trickiest one out of them all by looking at it visually. But really that's the trick there. You just have to remember go ×2. Put everything else in either this configuration or that configuration, and you're all set up.
So it doesn't matter. Well, it doesn't matter depending on where it says Z positive or not, but then you just double.
Exactly, yeah, absolutely. Other questions so far? Okay, well, we've got about 3 minutes. Not enough time to go through a full problem, even if we're trying our hardest. So this will be one we come back to on Wednesday's class. But by then, we'll have the entire procedure ready to go. So we'll be just running through these examples. Looks like 3 of them altogether. That might actually take a good amount of time. So we may finish these set of notes when we come back on Thursday. The bonus extra credit quiz is basically going to be one of these problems, change context and numbers. Well, have a great day, folks. Thanks for your patience on getting through this content. This is pretty tricky for a statistics class, but we're almost getting through all of it. So congratulations.